So thank you, Carlos. Actually, I was about to thank the organizers, but but I am one. I'm at least officially one of them. So so I will be more specific and thank Carlos and Guillermo for inviting me to organize and to talk here. So as Carlos said, I mean. My idea here was just to give a kind of a brief overview and on this class of logical formalisms with a two-layer syntax that have been proved, let's say, quite suitable to define logics to reason about different kinds of uncertainty. So let me check what happens now. Nope. Oops. Now, so actually, this, as I already told you, this was my aim, no, my main aim here, just to present you this in very simply what are these logical formalisms are about, and in particular, I would concentrate on one family based on Lukasiewicz logic, which turns out to be especially suitable or appropriate for modeling reasoning with probabilities. Although other let's say logics of this family can also be defined to reason about other uncertainty models like belief functions or imprecise probabilities that actually I would like to talk a bit at the end. Sorry because the arrows don't work for me neither. Okay, so I will start with a very brief, let's say, recalling about Lukasiewicz fuzzy logic and rational Pavelka logic, and then I will go into this two-layer logic where the inner logic for is the classical logic for where. So we will deal with probability of classical events, and then we will use Lukasiewicz logic as the outer or second layer logic in order to properly modeling probability. And also, as I mentioned at the end, I would like to show you also small variations of the same let's say framework in order to model reasoning with belief functions and imprecise probabilities that are somehow related still to probability, but they have different properties. Okay, so just okay, this I think it's quite well known, but let me introduce once more Lukasiewicz logic. Lukasiewicz logic was introduced many years ago by Jan Lukasiewicz. First with logic with over a finite number of values, and then later with Tarski was generalized to the infinite valued logic and with values in the real unit interval 0, 1. So there are also many equivalent presentations, but here I will choose the one with implication and negation as primitive connectives, and then there is this simple set of 4 axioms that axiomatize the logic. This logic, in fact, has a nice algebraic semantics, which is the variety of MB algebras, which are MB algebras are related to abelian order group, lattice order groups, as was studied in depth by Daniele, and probably he will talk about that in the last talk tomorrow, right? Yes, tomorrow. And okay, and this algebra is as a variety is generated by what is usually called standard MB algebra. So the MB algebra on the real unit interval, this 0, 1 MB, which where, let's say, the operations related to implication and negation are the ones here below. So the implication is this expression with mean and 1 minus x plus y, and the negation is 1 minus x. Okay, let's say from this primitive connectives, there are a lot of other connectives that are definable. I will show you some here. Together with their associated truth functions. For instance, the Chang sum, the Chang or strong OR connectives, which is this one has as the truth function this bounded addition. The strong disjunction is it's the Morgan dual, which turns out to be this truth function. Also, there is a kind of sort of subtraction. I mean, with this phi and not phi. This has as truth function this bounded subtraction, and then of course there are the lattice connectives. I mean, supremum and meet and join with min and max as truth functions. But I would like to remark that the characteristic connectives of Lukasiewicz logic has truth functions related to addition. So the addition is and subtraction, if you want. So these are its main, let's say, characteristic that we will exploit later for our logics to deal with probability. Okay. Of course, the logic is complete with respect to these semantics based on the algebra, on the MB algebra, and on the real unit interval, and is complete for deductions from finite set of formulas. So it's is not complete with respect to deductions from arbitrary theories. Okay. Okay. So as it is defined as and it happens as in most of let's say of systems of mathematical fuzzy logic, these logics are mainly qualitative in the sense that the implication captures the order. So when you derive an implication, phi implies psi, then it means that the truth values for phi, or sorry, for psi are at least as as big as the truth values for phi for every evaluation. So this is fine, but sometimes maybe if if one is interested in to allow a more, let's say, quantitative mode of reasoning with, for instance, with explicit truth degrees, then what one can do is, for instance, introduce truth constants into the language of Lukasiewicz logic, and for instance to be able to express inferences of this kind. So if some formula is greater, the truth of some formula is greater than 0.6 and another is greater or equal than 0.8, then the truth of their conjunction will be at least 0.4. And for that, actually, there is a logic which is known as rational PAVELKA logic, formally introduced by PAVELKA and then developed by Hayek, where you can introduce a truth constant for every rational in the unit interval, and then sorry, oops, oh, okay. Yeah, so it's okay, and with doing that, so you increase the expressive power of the logic, and it actually it has a very simple, let's say, is a very simple expansion of the logic. So it can be axiomatized by just adding to the axioms of Lukasiewicz logic this what they are called bookkeeping axioms. So basically, these are axioms. Keeping track of the intended semantics of the, for instance, in the case of the implication, right? So this bar denotes constant. Then it turns out that having these axioms, let's say, forcing the semantics to be the intended one for implication, then one I mean, can be from that it follows that the other semantics for the semantics for the other connectives are already can determine as well, and so that the completeness result for Lukasiewicz extends very say smoothly to this logic with truth constants. So again, if we have a finite set of or finite theory T, then from T follows phi, even only if semantically for every evaluation, and so that is model of T, then it's also model of phi. This logic also has another kind of completeness, let's say a more an infinitary version of completeness, just saying that the supremum of the values with rationals such that T derives R implies phi. This should be or is equal to the infimum of the truth values of phi that takes for every model of T. Okay, so here T can be arbitrary, but anyway, we will not use that. So sorry again for this is okay. So just after this short introduction of recalling basic facts about Lukasiewicz logic, let me just introduce this formalism with two-layer syntax in order to define logics to reason about probability. Okay, so the idea actually is quite old, from the 50s, and then Hayek took it over in the 90s. The idea is that if we want to reason about the probability of classical propositions here, okay, so what one can do is to introduce a modality P, where P phi is just understood as the expression phi is probable, okay, and it turns out, of course, that this expression phi is probable is not a Boolean expression, but a gradual expression. So it's very natural to consider that this phi is probable will be the truth of this expression will be higher as so the higher is the probability of phi, the higher will be the truth of P of phi. So even if phi is a classical Boolean proposition, then P of phi becomes a fuzzy gradual proposition, and actually we can take the probability of phi as the truth degree of P of phi. Okay, so but notice that here we are not mixing truth values with probabilities because the objects are different. The truth applies to this modality, while the probability applies to classical propositions. Okay, and this is the first, let's say, observation. And the second one is that that the probability laws, for instance, basically additivity, can be expressed using Lukasiewicz connectives. For instance, I mean, this expression says that the probability of the disjunction is the sum of probabilities minus the probability of the conjunction. Then this can be slightly rearranged by using, let's say, the strong disjunction of Lukasiewicz and that subtraction connective, bounded sums and bounded subtraction, right? In this way. So with what happens with probability can be done with other classes of uncertainty measures in the same way. So the idea which is behind this let's say fuzzy model approach to reasoning for reasoning with uncertainty is that basically we can encode in that case the laws of probability by means of formulas in Lukasiewicz logic, but involving the modalities P. Okay, so this is what is done here. Here. So basically, what we have is are these two layers. In the lower layer, we have, let's say, the logic of events, of classical events. We have all these propositions in the classical logic, and then what we do is that for every classical proposition, we can consider, let's say, a modal proposition, which will be, let's say, fuzzy. So for any classical one, we consider the P of we add the modality P in front of the proposition, and then what we have are these, let's say, set of atomic probabilistic formulas. So we have P in front of any classical expression, right? And once we have these atomic, let's say, modal formulas, then what we can do using Lukasiewicz logic is to combine them or close them by means of the connectives of the logic of Lukasiewicz logic. For instance, here we may have this P of phi and psi implies with Lukasiewicz implication P of high, right? Or if we have truth constants into the language, then, for instance, this second formula would say that the probability of not psi and high is at least 0.6. Okay, so we have these two separate layers in the syntax, and then, well, more formally, we have these two sets of formulas: non-modal and modal. Non-modal are classical ones, modal are the ones with the P atomic, and then we can combine them with Lukasiewicz connectives. But what we cannot have is somehow we cannot mix both sets of formulas. For instance, these formulas in the bottom are not formulas of the logic, right? Because here we mix a classical one with a P one, or we cannot allow also iterations of the modality P. Okay, so once this is done, then the axiomatization for these logics is quite simple, in the sense that we only have to let's say, gather axioms and rules for the low-level logic, also called inner logic, which stay for the logic of events. In here, it would be classical logic. And then we have we have to gather axioms of Lukasiewicz logic for the modal formulas. This will be the outer logic. And then this set of axioms are the ones basically that characterize, let's say, probability measures. Basically, here FP2 stands for the additivity property, finite additivity property. FP3, sorry, is what is saying is that the probability of not phi is 1 minus probability of phi, and there is this FP1, which is a kind of axiom K for pi, for P, sorry, which is valid, and, for instance, allows to show or to have that the P is so P preserves logical equivalence, right? Because if we have, on the other hand, if we would have here psi implies phi, then we would have the reverse implication here, and we would have the same probability for phi and psi. So this
Luis, 10 minutes.
Yes.
Including
10
questions.
minutes? Okay.
Thank you.
Okay.
Including questions.
Including questions. Okay. Sorry. So I will speed up. Okay. So whoops. So it turns out that this logic, well, semantics are given by probability Kripke models, where you have worlds together with the evaluations, classical evaluations, and some probability measure, such that the models of propositions are measurable, and then it extends using this would be for atomic ones, and then extends for compound formulas using Lukasiewicz truth functions. Okay, and of course the nice thing of that is that the logic is complete. with respect deductions for theories of these model formulas. So what what we can deduce here, basically, this tells you that the logic actually captures reasoning with probability, because models of here are given by probability functions. I will not go. I mean, I will not go. I mean, with the main idea of the completeness proof, because there is no time. But basically, what one does is to translate deductions in this two-layer logic to deductions into Lukasiewicz logic by means of some suitable translations, preserving the finiteness of the translated theory, because we can only, let's say, apply completeness of Lukasiewicz logic for finite theory. So in that case, it works. Basically, I mean, this is very easy, but I will not go more into details. Let me just mention, okay, let me just mention, maybe this can be interesting, that Baldi, Cintul, and Nogueda show quite recently that the well-known Fagin, Halpen, and Megiddo's probability logic can be let's say captured or can be interpreted into this two-layer logic FP. Mainly, it might be at first sight a little bit surprising, because in this Fagin, Halpen, Megiddo's logic, basically the formulas or basic formulas are just linear inequalities with integral coefficients, but thanks to the McNaughton theorem, which provides the functional representation for Lukasiewicz logic, the authors managed to define translation from one logic to the other, and vice versa, preserving the semantics. Okay, so let me just go into the into the last part. So as you can see, I mean, this idea of having these two levels can be somehow be very general, and basically what you have to have is an inner logic, an outer logic, and some modality, such that modality denoting, for instance, uncertainty, so that this L1 will be the logic over which we want to reason about the for instance, the probability or belief functions and whatever. And the outer logic, it has to be some logic able to encode or to represent, yes, to characterize the laws of our uncertainty model. And also, for instance, Cintul and Nogueda already did some more, let's say, general study of these logics of this kind from a more abstract point of view. But let me just go to the last part, just showing that the same scheme can be used, for instance, to capture reasoning with belief functions. Belief functions are mappings from, for instance, from classical propositions to 0-1, satisfying these two properties. The second one, you can see that here, this would be, let's say, the inclusion-exclusion property for probabilities, but instead of an equality, we have inequality. And sorry. And here, the main, the interesting point is that it happens that belief functions can be understood on formulas, on classical formulas, can be understood as probabilities on model formulas for some model logic, for instance, validating axiom D. And for instance, this, let's say, cumbersome, I would say, because this property too has to be verified for each n, not for a fixed, but for each natural n. So this, which seems quite involved, then it becomes very simply, it follows very simply just by combining the properties of the box operator, for instance, think of S5, and the properties of the probability for disjunction. So the idea here was just to move from this initial logic on Lukasiewicz, instead of having events being classical propositions, here we have events as propositions, for instance, as formulas in a S5 logic, no? The well-known modal logic. And it turns out, whoops, again here, it turns out that we have a very also quite simple axiomatization. Just we have to just replace the axioms for classical logic for axioms for S5, and then we keep the same probabilistic axioms because we are dealing with probabilities of boxes. So now here this phi and psi can be model formulas, and then it works. I mean, so for you can prove that for finite, again, for finite theories of formulas of this kind of B phi, which is just P of box phi, then actually deductions in this logic is actually captures reasoning with belief functions. And just the last thing is that so we have seen that for belief functions we replaced the inner logic that was classical logic by for instance S5 modal logic. Now it happens that if you want to capture reasoning with imprecise probabilities, which is just instead of having just one probability, you have a family of probabilities, and you have then, let's say, lower and upper estimates of the probability of propositions, then it turns out that what you have to change is not the inner logic, but the outer logic. So, and this, in particular, the outer logic was that was Lukasiewicz logic in the first case. Now we replace it by a modal logic over Lukasiewicz logic, which is an analog of the S5, so satisfying the usual S5 axioms, but over Lukasiewicz logic, because there you can restrict yourself to work with Kripke models where the accessibility relation is the universal one. So every world is related to any other world. And then the evaluations of box in that logic, it becomes the infimum of all possible evaluations. So when we come here, when now we have this proposition being a P formula, so that we have box of P of phi, then what the evaluation in one such a model, if we have probabilities for every world, then it becomes the infimum of probabilities in the model. So, and yeah, and then it also turns out to work. So here again, we have the same scheme. We have axioms and rules for the inner logic, which is classical logic. We have axioms and rules for the probability formulas, which we already had, and we have axioms and rules for this modal Lukasiewicz logic. And then what can be shown that this is basically is ongoing work by Corsi, Flaminio, and Hosny. So they can show that deductions in this other two-layer logic captures reasoning with, for instance, lower probabilities. One could do the same with upper probabilities by using the diamond. Okay, so how much? Sorry, I skip just the.
Yeah, Lluis, it's time really.
Is already time? Okay. Okay.
Yeah.
Well, this is the conclusions. I let them here if you want to read it. So okay. So thank you.